Even with considerable investment in flood defenses, flooding is a very real risk, as we know only too well. Every year floods cause billions of damage and take hundreds of lives. Floods occur in all continents and countries, rich and poor. While we cannot completely prevent flooding, we can minimize the chance it occurs by maintaining and improving our flood defenses. And we can minimize damage and loss of life by taking adequate and immediate measures in the rare event that a flood defense fails.
The Intergovernmental Panel on Climate Change believes that by the year 2100, sea levels could have risen by 59 centimetres. Now, close to 500 million people live on or near a delta region. That's where the river meets the sea. And the expanding global population would be at risk of flooding, retreating shorelines and subsidence. Indeed, the problem is so severe that over the course of this century, 187 million people could be displaced. That would be 2.4% of the global population. It puts at risk huge important cities like New York in the USA, Dike in Bangladesh, and the expanding coastal cities of Asia.
The latest initiative involves developing the next generation of smart dikes to provide accurate early warning systems. UrbanFlood is an EU-funded project that involves a number of businesses, including the Dutch applied research company TNO.
Where increasing the height of flood defenses is no option because of cost and lack of space, like in urban areas, other solutions have to be found. In such cases, the answer may be in continuous monitoring of the flood defense with modern sensor techniques. Such sensors give detailed information on the behavior of the dike. They allow you to look inside the dike. Several sensors were tested during the Dike experiments. Typically, they will measure temperature, water pressure, acceleration, and tilt or angle. At this moment, a number of regional water management authorities in the Netherlands are taking this to the next step: trial implementation in dikes, from a few hundred meters to possibly 22 kilometers. Now, imagine that hundreds of kilometers of dikes are equipped with such sensors. These sensors will produce an enormous amount of data. The data are transported using the internet, allowing access from all over the world, and stored in a so-called common information space. Then the data are validated and assessed using artificial intelligence. Artificial intelligence can be trained to recognize data that indicate a normal, safe situation. Any data points that are outside these safe boundaries are flagged, and experts are alerted. If the situation is safe, the safe boundaries are changed to include the flagged data points. However, if a potential unsafe situation is recognized, a cascade of models will be started. First, the stability of the dike is assessed. If the risk of breaching is significant, the breach model is started. Results from this model are used in the rapid flood spreading model, after which the life safety model may be used to assess the risk of casualties and the options of evacuation. In the present urban flood early warning system, prototype models are used. Other models can be adjusted to be used within the urban flood early warning system. The models run in the cloud, and computer capacity can be added when required, which enables what-if scenarios and multiple simultaneous runs with different parameters. All this together is the urban flood early warning and decision support system. It can be accessed using standard web browsers and handheld devices, but the system is specially designed for use on a multi-touch table. Multi-touch surfaces allow medium-sized, multidisciplinary emergency action teams to access all relevant data and work on it as a group. Information is literally at the tip of their fingers, easily manipulated and shared. It is possible to see a satellite image of a flood defense object, to see video from cameras installed there, and of course to see the data from any sensor you select. Combining sensor graphs for comparison is easy. And the behavior of a breach and the spreading of the flood in case of a breach can be shown. This allows emergency services and authorities to decide if an evacuation is needed and to where to evacuate, which areas to evacuate first, and how long roads are passable. In addition to the early warning model cascade, a virtual dike model has been developed. With this finite element model, the behavior of a dike can be modeled. Data from sensors can be analyzed and the results can be used to train the artificial intelligence module. The next step is to test UrbanFlood early warning system in a real operational setting. With the rapid improvements of sensor technology, computing, communication and the internet, we do believe that we have a prototype of the flood early warning system of the future.